So our next mini seminar is on synthetic data, and it's going to be given by Boris van Breugel. Boris is a PhD student who joined our lab last year. And Boris, whenever you're ready, please go ahead and share your screen.
Thank you, Nick. Hi, everyone. My name is Boris van Breugel, and I will be talking about synthetic data. So before we talk about synthetic data, let's talk about real data. So in the healthcare setting, if you are a data holder like a hospital, it is actually not that easy to share your data with, for example, the machine learning community. And mainly this is, so basically there are these strict regulations in place, which is mainly due to privacy concerns. Of course, this makes a lot of sense, but because there are these strong regulations, in the end, it leads to a situation where there is a lack of high quality healthcare data, which in turn impedes ML research in healthcare. So there are two ways to solve this. The first one is to de-identify or anonymize data, which basically means to, for example, remove your name and your postcode and other features that we think are irrelevant actually for what we are trying to do, but are still in the data. Of course, the problem with this idea is that that doesn't give any guarantees on the data actually being private. So another option and a better option is to create synthetic data, and which means that you create data from scratch. So just from random noise, you generate data. And the idea is that it cannot be synced back to the individual if you do it well. Of course, it's not easy, though, to just generate data that looks like real data, but is in fact fake data. So to do this, we actually need machine learning. So we need machine learning so that we can enable more machine learning. That's the idea behind synthetic data. So what's the advantage of having synthetic data? For one, it allows you to do more analytics on this data. So instead of needing real data to do your analytics, you can just publish your synthetic data and other people can, for example, analyze it and draw conclusions from it. Secondly, it can facilitate reproducibility. Of course, if you have private data, no one can reproduce your data. So again, having this synthetic data that looks like real data for your analyses is advantageous. Thirdly, and this is kind of interesting, is there might actually be a problem with your data itself. For example, there might be some groups that are underrepresented in your data. If you can actually generate synthetic data, you can just keep on generating data for these underrepresented groups, or for example, for rare diseases, resulting in a more balanced population. And fourthly, in the end, it can also lead to stronger models. For example, consider multiple hospitals that all have their own data and try to use this. Well, wouldn't it make more sense if they can share it somehow and thus build a stronger model? So these are the more classical applications of synthetic data. However, today I'm going to talk about something else, and that is to generate fair data based on unfair data. So here the idea is as follows. The problem is that real data might actually contain bias. So for example, if you look at loan application data, there might be bias between ethnicity and whether someone gets a loan. And if you want to publish your data, you don't want this bias to be in there. So the aim is to create fair synthetic data based on this real unfair data. So what do we propose? We propose a model called DECAF, which uses causal knowledge in generative adversarial networks to generate this fair data. And this was a collaboration with Trent Kiono, Jeroen Barrowfoots, and Michaela van der Schaar. It's just been accepted to NeurIPS. So what is the motivation here? So if we have unfair data, this could lead to the models that we train on the data to also give unfair predictions. So consider in this example, whether someone gets a loan. Here we would use ethnicity directly in predicting whether someone gets a loan, which is of course problematic. So one thing that people might propose is to simply remove the variable ethnicity. However, this does not really solve the problem, because you would still have, for example, bias that goes via other variables, in this case, married. So the model that you train to predict whether someone should get a loan is still dependent on ethnicity indirectly. So what we want to do is to have guarantees of the fairness for the fairness of our downstream models at the data level. So let us look at how DECAF works. It consists of 4 steps. And basically, we assume that we already know or have already learned the causal structure of the data. So what does that mean? Consider this simple example where we have the protected variable A, for example, gender, and Y, which is for the target, which is, for example, whether someone gets a loan. Then there's other variables that are affected or cause these protected variables and the target variable. In this case, the first step is to simply train a generative model based on the causal structure of the data, which would look as follows. This is a GAN structure, a generative adversarial network, but any model can be used. The idea here is to generate a feature based on its parents. So for modeling B, we use A, and for modeling Y, we use all its parents. So we train a model to generate data using this causal structure. Subsequently, we look at the graph and we define which edges constitute to unacceptable bias. And of course, this entirely depends on what definition we are using. So for example, if we don't accept direct bias, we only remove this edge. Whereas if we don't accept indirect bias, we also need to remove the edge from B to Y and C to Y. So when we have removed those, we can just take our old model, which we have already trained, but now instead of using D, A, B, and C to generate Y, we only use, for example, D, B, and C. In our paper, we give some guarantees that this indeed leads to the downstream model being fair. So here are some results in which we plot, tabulate both the data quality and the fairness against different methods. And what we see, astonishingly, is that actually DECAF performs remarkably well both on data quality and the fairness. So if we look at the data quality, we see that DECAF, and this is DECAF for different definitions of fairness, which leads to different edges being removed, that DECAF actually performs really well, both in terms of the quality of the data itself, as well as the downstream performance. Also compared to, for example, baselines that don't even do fairness, like the WGAN GP. When we look at the fairness, we see that for different definitions, we can guarantee fairness. So if we want to have just FTU fairness, which basically means no direct discrimination, we can actually create that. If we also don't allow indirect discrimination, we also can achieve that, but with a different DECAF model, so different edges removed. Here, without going into much detail, we show that even if the bias increases, DECAF performs remarkably well. So the conclusion of this is that DECAF can generate fair synthetic data based on unfair real data, and that it is compatible with different definitions of fairness. So in the end, this gives a versatile model for people who own data to generate fair data and to publish this data with guarantees for the downstream model performance and fairness. And in the end, we saw experimentally this data quality is very well preserved. So today I only spoke about fair synthetic data, but the lab has done a lot of work on, for example, private synthetic data. If you are interested in this, please have a look on the website where we propose tools, evaluation metrics, and a vision for synthetic data. Thank you very much.